Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on AC and electromagnetic induction. And this question is from October-November 2021, paper 4, variant 2. In this question, we will discuss a lot of important concepts and I will explain you those concepts in detail. We will discuss what is the function of iron core, why do we need iron core in transformer, and why iron core is laminated. And a lot more we will discuss in this lesson about AC and EM induction. For part A1, we need to state the function of the iron core. Means why do we need to use iron core in transformer? And this question is very common in past papers. Most of the students, they can answer this question easily by just memorizing the answer. But they don't understand the reason behind the answer. So in today's class, I will explain you the reason behind using iron core. Means why do we use iron core? So let's try to understand first of all some properties of iron. Iron has high permeability. High permeability means high value of mu naught. So it has high permeability. High permeability also means that low reluctance. Low reluctance. So simply we can say low reluctance. So iron has low reluctance. As iron has low reluctance, magnetic flux prefers. So you need to understand magnetic flux prefers low reluctance path. Low reluctance path. So this is the main point you need to understand. Low reluctance path. This is very similar to electrical circuits. Let's try to understand this one with the help of electrical circuit as well. Let's say we have electrical circuit and this circuit has one battery and two resistors. Imagine that the resistance of one resistor is 100 ohms and the resistance of second resistor is just 1 ohm. In this case, most of the current will pass through 1 ohm resistor. This current will be around 100 times greater than this current because current prefers low resistance path. Current prefers low resistance path, but magnetic flux prefer low reluctance path, low resistance path. So this is the main concept. You can also compare this one with electrical circuits. So magnetic flux prefers low reluctance path, and this is the main concept behind using iron core because iron core has very low reluctance. So in this case, if you look at this picture, in this case you can see we have just air. So a lot of magnetic flux is wasted. Means magnetic flux leakage in this case. A lot of magnetic flux has been leaked. We can say magnetic flux. A very few magnetic flux pass through this secondary coil. So you can see, if you look at this secondary coil, you can see very low magnetic flux is passing through this secondary coil. So in this case, the efficiency of transformer will be very low. Efficiency will be very low. In this case, efficiency will be very low because for ideal transformer, our assumption is that for ideal transformer, our assumption is that flux in the primary coil is almost equal to flux in the secondary coil. Means the flux in the secondary coil is almost the same flux in the primary coil. So this is assumption for ideal transformer. Means when we assume efficiency of the transformer is 100%. But if we don't use iron core, then flux in the primary coil and flux in the secondary coil, they will not be same. Flux in the secondary coil will be very, very low as flux in the primary coil. So efficiency of the transformer will be very low. So that's the reason we have to use iron core to increase the magnetic flux linkage between the coils. So this is the main purpose of using iron core to increase the magnetic flux linkage between the coil, or you can say magnetic flux between the coils. Now let me show you how you can write down the answer. The purpose of iron core is to increase the magnetic flux linkage between between the coils. Let's try to understand a little bit more about this one, then we will go to the second part. If you look at this transformer, this is our ideal transformer, and this transformer has iron core. Here is the primary coil. So the first one, this is the primary coil. This is connected with alternating power supply. So this is primary coil, and here you can imagine this one is the secondary coil. So this one is secondary coil, so we can say VS. So this is our secondary coil. If you look at these two coils, in this case you can see magnetic flux here in the primary coil and magnetic flux in the secondary coil is almost the same. Why this magnetic flux is the same? Because iron core has low reluctance. So the magnetic flux in this case, it will not escape to the air because air has high reluctance. So the magnetic flux will be captured by the iron core and it will stay in the iron core. So in this case, magnetic flux in the primary coil and magnetic flux in the secondary coil will be the same. So that is the main reason. So iron core will capture the magnetic flux and magnetic flux will not escape into the air because air has high reluctance, and magnetic flux prefers low reluctance path. So flux will stay in this iron core. So the flux in the primary coil and in the secondary coil will be the same. So this is the reason behind using iron core. For the second part, we need to explain why the iron core is laminated. First of all, let's try to understand what does it mean by laminated. Laminated means that we have one layer of iron. So this is one layer of iron. Then we have one layer of insulating material. So we have another layer of iron. And between these two layers, we have layer of insulating material. So I'll be using here. So this is layer of insulating material. So you can imagine between these two layers, we have insulating material. So here we have insulating material. So here is insulating material, layer of insulating material. And this kind of arrangement we call is laminated iron core. So this is iron. Here we have another layer of iron. So this is iron. And between these two layers, we have insulating material. So this is how laminated iron core is made. Laminated iron core is made. So this is also insulating material. So laminated iron core is made in layers. Now we need to understand what is the benefit of laminated iron core. If you look at this iron core is also conductor. So the first thing you need to understand, iron core is also conductor. So simply we can write down iron core is also conductor. And this conductor is inside changing magnetic field because this is alternating power supply. So the magnetic field in this coil is changing. So the magnetic field inside this iron core is also changing. So we can say this iron core is inside changing magnetic field by electromagnetic induction because conductor is inside changing magnetic field by electromagnetic induction principle. Induced current will produce, current will be induced. So we can say induced current. And that induced current in the iron core, induced current in iron core, we call is eddy current. So that current we call is eddy current. Eddy current. And this eddy current, this will cause loss of electrical energy. So there will be power loss. We can say P, this is equal to I square times R. Now in this case, our main goal is to reduce eddy current. Means we need to reduce this current. So how we can reduce this current? In order to reduce this current, if you look at this setup of laminated iron core, in this case current can only flow in the iron, but current cannot flow in the insulating material. So in this case we limit or we bounded current only in iron core. Or in other words, we can say we have decreased the current. So in this case we have decreased the current. As current has decreased, so it means the power loss has been decreased, and this current is eddy current. So we can reduce eddy currents by using laminated iron core, because in laminated iron core current can only flow in the iron, but current cannot flow between layers. We can also write down current cannot flow between layers. Current cannot flow between layers. Cannot flow between layers. Between layers. As current cannot flow between layers, in this case we have reduced current. As we reduce current, so the power loss also has been reduced. So this is main purpose of using laminated iron. So 2 points we can mention in this case. First thing, we reduce eddy current. So when eddy currents are reduced, power loss is also reduced. Now let me show you how you can write down your answer for this question. So in your answer, you can mention to reduce energy losses by reducing induced currents. Induced currents means eddy currents. Eddy currents. So this is main purpose of using laminated iron core. For part B, we need to calculate the maximum value of Vout. But for this question, it is given to us the input PD V in is the sinusoidal alternating voltage of peak value of 1200 kilovolts and period is 40 milliseconds. We need to calculate maximum value of Vout. We have to calculate value of Vout. For the primary coil, number of turns are given. We have 25,000, and for the secondary coil we have 625 turns. So simply in this case we have to use Vp over Np. This is equal to Vs over Ns. We have to calculate Vs, maximum value, peak value. So simply we can rearrange this one. We can write down Vp over Np times Ns. This is equal to Vs. Vp in this case is given to us and its value is 12,000. Np is 25,000. We have to multiply this one with number of turns on secondary coil, that is 625. If we simplify this one, our final answer will be 300 volts, and this is the maximum value of Vout. So simply we can write down this is 300 volts, and this is our answer. This question has only 1 mark. If you have got the right answer, you will get this mark. So one thing you need to understand, if Vp, very important point, so let me highlight here. If Vp is peak value, means you're using peak value of Vp, you have to use the peak value of Vs as well. But if you use RMS value here, if you use RMS value, then you also need to use RMS value of Vs as well. Very important point, you have to be very clear about this. In this case, we have peak value of Vp, so we also got peak value of Vs. If we use here RMS value of Vp, we will also get RMS value of Vs. For the second part, we need to calculate the root mean square current in the load resistor. In the load resistor, now you can see we have calculated value of Vout. Vout is equal to 300 volts. It simply means that if you connect voltmeter across this load resistor, the reading on this voltmeter is 300 volts. Now we need to find the current in this resistor. Resistance of this resistor is given to us. We need to find out IRMS. IRMS, it means we have to use RMS value of the V, and simply you need to divide by resistance of resistor. VRMS. So now we need to understand the relationship between VRMS and the peak value. V peak, if you divide this one by root of 2, this one is equal to VRMS. Now we can plug in this value here, so we can replace VRMS with peak value. So V peak divided by root of 2 times R. V peak, we have the value of V peak is equal to 300, and we can divide this one by root of 2. And we have to multiply with resistance of resistor, that is equal to 640. Now if we simplify this, our final answer is 0.33 up to 2 SF, and this is our final answer. So simply we have to write down our answer here up to 2 SF. If you got got the right answer, you will get this A mark. For the third part on figure 10.2, we need to sketch the variation with time t of the power P dissipated in the load resistor from time t is equal to 0 to t is equal to 40 milliseconds. 40 milliseconds actually is the time period. So we can say 40 milliseconds is equal to time period. It is also given to us. We can assume that P is equal to 0 when t is equal to 0. It simply means that when t is 0, P is equal to 0. Now we can find out, first of all, P max means the maximum value of P, power dissipated. That one will be equal to peak value square times the resistance. But we have already calculated IRMS. So if IRMS we can calculate I peak. I peak will be equal to root of 2 times IRMS. So we can replace I peak with root of 2 times IRMS. Square of this multiply with R. Now simply we need to plug in values. So we have root 2, this is multiplied with RMS value, that was equal to 0.33. Square of this, and we have to multiply with resistance of load resistor, means with this resistance. And resistance is equal to 640. If we solve this one, our final answer will be 138.5. So approximately we can say this is equal to 140 up to 2 SF. Up to 2 SF, this is 140 watts. So this is peak value. Now the second thing we need to understand, power is a scalar. Power is scalar. Now if we sketch a graph for current against time, let's say we have current here. So this is current. So when current is here, so this is current with time. Time is in milliseconds. Current direction is positive and negative. But if we sketch a graph for power against time, so we can understand the shape of the graph. Power is in watts. And here we have time. This is in milliseconds. We need to understand when current is positive, power is still positive. So power, the shape of the graph is sinusoidal. But when current is negative, power cannot be negative because this is equal to I square. So this will be again positive. So this will be the shape of the graph. And we have already find the peak value, that is equal to 140. So half of the period is here. So power at this point again will be 0. Power at this point again will be 0 because current is equal to 0. So now we have peak value. We have the value of P at 20 milliseconds. We have value of P at 40 milliseconds, and we have value of P at 0. And we also understand this will follow sinusoidal curve because current is following sinusoidal, so power will also follow sinusoidal curve. Based on this one, we can sketch our graph. So this is how you can sketch. And so this is shape of the graph. So the peak value, this is important point. This has 1 mark. Peak value is equal to 140 watts. So this is how you need to sketch. If you sketch like this, you will get 3 marks. This question has 3 marks. For part C, we need to explain with reference to figure 10.2. And this is our figure 10.2. So this is figure 10.2. We need to explain why the mean power in the load resistor is 70 watts. If you look at mean power and the peak power, we can find the relationship between these two. Mean power is equal to half of the peak power. So we can say peak power. If you divide this one by 2, we can get mean power. Peak power was equal to 140. If you divide this one by 2, we can get mean power. So in this case, simply we can say mean power is half of peak power. Now we need to explain this one, why mean power is half of peak power using figure 10.2. We have to use this figure and we need to explain. So the best way to understand this one is look at these areas. I have already highlighted these areas. You can see this area is yellow and this area is blue. These two areas, they are almost equal. equal. If we draw the line here, if the power was 140 all the time, it has to follow this horizontal line. So then the area under this one is equal to area of rectangle. So we can draw the rectangle here. So this will be the area of the rectangle. If the power was all the time 140, but power is not 140 all the time. If we look at figure 10.2, simply we can find out the power is changing between 0 and 140 watts. Means the power dissipated in the load resistor is changing from 0 to 140 watts. Now if we look at areas, yellow area and the blue area, we can see that these two areas means the blue area, this is equal to yellow area. If power was 140 all the time, then the area has to be equal to area under that horizontal line has to be equal to area colored blue plus area colored yellow. So then we can say the mean power is equal to 140. But in this case now, blue area is equal to yellow area, so the mean power is equal to 70 watts. Or simply we can say why blue area is equal to yellow area. The reason is because the power curve is symmetrical. So we can say power curve is symmetrical. That's reason these two areas are equal. And the mean power dissipated is equal to 70 watts. So this is the point we have to write down in our answer. So let me show you how you can write down your answer. This is how you can write down your answer. If you write down these 2 points, you will get 2 marks. Power curve is symmetrical about the midpoint on the power axis. So it is symmetrical. So you can see it is symmetrical. And mean power is half of the P power. If you write down these 2 points, you will get 2 marks.